Hello. In this video, I am going to demonstrate with a simulation using Excel Le Chatelier's principle. Le Chatelier's principle states that when you place a stress on a system at equilibrium, the system will shift to a new state of equilibrium, at least if it can, and it will shift in such a direction that will partially undo the effect of the stress. We're going to use the effect of pressure changes on systems at a system at equilibrium in this simulation. Okay, so let's imagine we have an equilibrium between a dimer A2 and the monomers that make it up, A2 in equilibrium with A. And let's imagine that this is an equilibrium mixture. In this particular mixture, let's just say it happens to have an equal number of A and A2 molecules. It's at such a volume that that's the case, all right? All right, now let's suppose we suddenly make the volume much smaller, keep all these molecules in a much smaller by applying a pressure. So now we have there were 20 molecules to start with. There's still 20, 10 and 10, before it has a chance to readjust. And it's no longer at equilibrium once we do that. And so it's going to shift in such a direction as to partially undo the effect of the stress. The stress was to increase the pressure, and by the 2A producing A2, we are reducing the number of molecules in the system. And so the new state of equilibrium, let's say, is something like this, and there are fewer molecules and a greater proportion of A2 relative to A. So the system is in a new state of equilibrium, and it has partially undone the effect of the stress. By reducing the number of molecules, it has reduced the pressure from what the stress put on the system. Okay, here's the Excel simulation. And in doing the simulation, I have an equilibrium between A2 and 2A and A. And the rate constant for the forward reaction, Kf, in this case is 0.04, and the reverse 0.01. And these are the equations for the kinetics of the reaction. This is how A2 changes with time. This is how A changes with time. And we bring the time to the other side, make each increment 1 second. Our K's are small enough that 1 second is a small enough interval. And we can have a simulation of how the concentration changes with time. In the first example, the initial concentration of A is 4 molar of A2, and the concentration of A is 0. And when they reach equilibrium, you can see it turns out there's 56% A, and the rest is B. I just want to show you that if you change, I'm going to go over here and change the concentration of A from 4 to 2. Let me change it from 4 to 5. And remember, it was 56% A. By making the pressure higher, the percent A decreases, all right? Okay, it decreases. Okay, I'm going to go back to 4. And now let's change the volume at 50 seconds. I'm going to change it from 1 liter to 0.5. I'm going to stuff all those molecules into a smaller volume. It's probably going to go off scale. So let me make this 2 first. Okay, so now I'm going to make the volume 0.5. And so at 50 seconds, the volume halves. Of course, the pressure doubles. All right, concentration doubles, and it's no longer at equilibrium. And by increasing the pressure, we're having the system having to adjust, and it adjusts in such a way that there's less A and more A2. You can see it went from 67% A to 56% A. Okay, so there was an increase in the pressure and stuffing the same number of molecules in a smaller volume, it adjusts by going from 2A to A, shifting to the left. All right, let's do it again. Let's make another decrease at 100 seconds. I went a little off scale, but it comes back. Well, it doesn't really. Let me change my scale to 8. Okay. And now, with this higher pressure yet, the percent A is 46%. Now, let me go the other way. In the last increment, let me double the volume. So I'll put a 2 liters, and you can see that the equilibrium shifts in the other direction now, and we went from 46% A to 56. Okay, so this is a nice little simulation that illustrates Le Chatelier's principle. You need a reaction in which a gas reaction, and in which the number of the stoichiometry is such that there's not the same number of moles on both sides. There's 1 mole here and 2 moles here. So if it were 1-to-1, you wouldn't get this effect. So I hope that's useful and informative to you, and I'll see you next time.